All right, let's go on to the second proof, or the second way of showing that A equals V squared over R. So uniform circular motion. I don't really care about my handwriting at this point. So we're going to redraw our two circles. This one looks good. And over here we'll draw one for velocity. And so in position world, whoops, there we go. Position space. There's the circle, the center. And so we're going to take, basically we're going to take it two different times that are some, time apart. You're going to take position vector at time 1, we're going to call R1, and position vector at time 2, we're going to call R2. And then let's go ahead and draw our velocity vectors for those two, just to sort of flesh it out a little. So there's velocity vector at time 2, which we're going to call V2, and velocity vector at time 1, we're going to call V1. So over here we can draw these, and I'm not drawing to the same scale, but I think you guys can forgive me that. So there's V1 and there's V2. So right, so at time 1 it's here and it's going this way, so there's V1, and then at time 2 it's moved here and it's going this way, so there's V2. Alright, so where do we go from here? First thing we want to do is we want to complete this triangle and find the change in R over this period of time, which is, no, that's not very good looking, whoops. So there's our arrow, give or take, which is delta R. That's not very pretty either, so let's call this delta R, is that down there. So that's the change in R. It's completing this triangle, and that equals R2 minus R1. That's just the change in R from time 1 to time 2. Now, can we find delta V over here? Why, yes we can. So let me just do this and say delta V equals V2 minus V1, and that is this right there. Okay? So we have now delta R, delta V, R1, R2, V1, V2. Alright, so let's go a step further, and we know the magnitude of R1 is just R, the radius of the circle, and so is the magnitude of R2. Right? That's circular motion. It's always got to be the same distance from the center, so the magnitudes of both of these position vectors, which we measure from the center, are R. Well, can we say the same thing for velocities? We sure can. Remember, this is going at uniform speed, so that means the magnitude of velocity at time 1 equals the magnitude of the velocity at time 2, which equals the speed, little v, or not little v, but scalar v. Okay, so we know that. Now, this is looking kind of suspiciously like these are both the same, or many things are the same about these. And what I want you to buy now is this angle here between these two, and this angle here between these two are the same. This angle and this angle are the same. Now you can see that by saying, well, you know this angle here is something. This one is a right angle, the velocity vector is at right angles here. This velocity vector is at right angles here. Right, if you extend this position vector, and then the velocity vector is a right angle, you extend this position vector, the velocity vector is a right angle. So, and these are the same vectors. So it stands to reason, I think you can see that these two angles between, the vectors in each circle will be the same. I'm going to call this, and you'll see why in a minute. I'm going to call this 2 theta. Okay? Or actually, you know what? I'm going to go one better than that. I'm going to call it, I can't do that. I can't erase that any further. You know what? Forget the 2. I'm going to call it delta theta. So it's the change in theta over some change in time. And so delta theta. All right, looks good so far. Those two are equal. So what can we prove now? Well, guess what? These are similar triangles. Why? Well, they're both isosceles. One thing. We know, so that an isosceles triangle has two identical legs, right? Well, each of these has two identical legs, and then they have the same angle between the two identical legs, which means they're similar. Both triangles are isosceles. Not isoscelers, sorry. Isosceles with identical, I'm not sure what you call it, but we call it identical angles between equal sides. This is the sort of sloppy math shorthand that I got into when I was taking geometry in 10th grade or 9th grade. But both triangles are isosceles triangles with equal angles between, or the identical angles between their equal sides. What that means is that triangles are similar. And so from there, well, you can say all kinds of interesting things. For one thing, you can make some ratio statements here. And now you can say that this delta r vector divided by the magnitude, well, actually what you can say is the magnitude of the delta r vector. So this here, magnitude of this here, divided by the magnitude of one of these legs, which is just r, either of these legs, is going to be equal to the magnitude of your delta v vector divided by one of the legs of the v triangle. There we go. Okay. Well, now this is getting interesting. So we can say, let's see, let's pull this apart a little. We can say 1 over r times delta r, magnitude delta r, equals, and I'm writing this a little funny for a reason. Well, I mean, everything I write is a little funny, right? But 1 over v times delta v, magnitude delta v. Let me just scroll this down a tiny bit so I have a little more space to write. There we go. That's good. Equals magnitude of delta v, right, times 1 over v. Okay, now we're going to divide, what we're going to do here is we're going to divide both sides by delta t. Okay, so now we've got our, what's delta r over delta t? That's just velocity, right? So this is our velocity vector, except we're taking the magnitude of our displacement. So really this is going to give us the magnitude of velocity. We can take, if we take a vector and divide it by a scalar, the magnitude of that is going to be the same as if we just taken the magnitude of the vector first and then divide. So what this tells us then is that delta r over delta t, so 1 over r times the magnitude of our v vector, okay, that's just what this is, equals 1 over v times the magnitude, and then what's delta v over delta t? Well, that's just delta a, right? Or sorry, that's just a, is that, okay? And you know, our standard relationship is you know, our standard notation is just use scalars to mean, actually it should be like that, to mean you know, the magnitude of a vector that have the same letter as. So v over r equals a over v, and that's where we were before when we were just looking at the circles, if you recall. So this gives us a equals v squared over, well, it's almost where we were. I mean, we have it upside down this time, but that's actually good because that's where we want to go. A equals v squared over r. And then we are done. So that's the second way to prove it. Third way is calculus, and I'll get there in the next video.